Hello and welcome to this PD session on skills-based science. This is essentially the same professional learning information that is being presented in a face-to-face session to teachers at the Hampton Ed Center today. But I wanted to get the same message out across the district, and this seemed like a reasonable way to do it. I've not tried a PowerPoint over YouTube type presentation before, so I'd appreciate any feedback that you have. If you find this useful or not, let me know and we can change things or enhance things a little bit as we go forward. Want to spend a little bit of time just taking a look at the upcoming grade 10 science field test. Want to take a look and revisit, I guess, those outcomes we called skilled outcomes or skills outcomes for grade 9 and 10 science. And as we meet face to face, we'll be sharing some ideas of how teachers are integrating those skilled outcomes into their classes, and I've inserted a few of those into this presentation as well. So I want to, before we go ahead and talk about the new grade 10 assessment, I thought it might be useful just to kind of take a look backwards at how we have been assessing up until this point. And if you look down through here, you can see it's kind of a crazy merry-go-round that the assessment branch has been on over the past 10 years, where they assessed at grade 2, grade 3, a couple of times at grade 4, 3 times at grade 5, 7, 8, 9, and then a number of times through high school with these different subject areas. And it was just felt that it was, they would just get one assessment out of the way and the next one would be coming up, and there was no real continuity to it. It was just kind of a merry-go-round existence. So starting last year, they've revised how they are going to be assessing students. So this is where we are in New Brunswick starting this year. All students in grade 4, 6, and 10 are being assessed pretty well right across the board: reading, mathematics, science, and French oral proficiency. And it's being done on an annual basis to all students, and it's happening in May. So this does a couple of nice things. First, it allows us to track those students, that same group of students going through from grade 4 to grade 6 to grade 10. So it gives us some longitudinal data. The other thing that's nice for those of you that teach high school is that this is the first time in a while that we've had any sort of benchmark for scientific literacy in the high school. So it's nice. It'll be nice to see some of that data and see where students are at that grade 10 level. So this rolled out last year, starting with the grade 6s, and last year the grade 6s did the field test, which is what the grade 10s will be doing this year. And the field test is really a test of the test items themselves. It's not a test of the student's ability. When the tests are marked, they won't be marking the students. What they're doing is marking the items to make sure that the items are fair, to make sure that the items are giving them the data that they are looking for. So if students are nervous, you can put them at rest a little bit, or if teachers are nervous, you can help them to advise them, I guess, that this is not a test of the students, this is a test of the test itself this year. As I say, the grade 6 went through that last year. Started out with about 130 questions. Not that every student wrote 130 questions, but there was an item bank of about 130 questions, which will get probably cut in about half for this year's grade 6 assessment. The other nice thing about the test is this. The format is a lot nicer than tests that have been written in the past. Each student receives one booklet. This is they call this a matrix format, I guess. Each booklet has just 13 multiple choice questions and 1 constructed response. So even though they have this fairly large bank of questions. Not every student is going to do every question. So what it means is that instead of having to write a 2 or 2.5 hour exam type thing, it's something that can be administered in a single period. So this year, for grade 10, because we are field testing, we'll probably have more than 4 booklets. But again, each student will only write 1 booklet. So you'll get, if for your class standing in front of you, you'll have 7 or 8 booklets to pass out, and student A will get booklet A, student B will get booklet B, student C will get booklet C, and they just write that 1 booklet, pass it in, and at the end of the hour they are done. This allows them to field test this large number of questions, and as I say, they'll probably end up throwing out about half of the questions, keeping the other half. And for 2016, when they implement the test for the first time, there'll be 4 booklets, each with different questions, but it'll be 13 multiple choice and 1 constructed response for the science section, designed to be done in a 1-hour period. What the test will look like in terms of content is about 20% on initiating and planning. These are all skills-based outcomes, by the way. So the framework that this will be in will be these big picture conceptual understandings. So it will be, you'll be able to tell it's a science test. So when we talk about performing and recording, it'll be performing and recording as it relates to some aspect of science. The same with analyzing and interpreting. The students will be asked to analyze and interpret scientific data or the results of some experiment that will be spelled out for them. So it'll be all done within a science curriculum framework, but the items that will be tested will be very much skills based. And then there'll be and then the final 10% there is on that communication and STSE part. So what the questions will look like, for those of you that are familiar with PISA type testing, and I know we've got PISA coming up this year, and the focus is science. So good fortune, I guess, that both these things are kind of happening at the same time. This is a question that I actually pulled off of an old PISA exam or some PISA practice questions. There's a little bit more background information, but essentially it's a water treatment facility. You can see there's a head pond there and a settling tank, and there's the treatment and the screening and the testing facility that you see there in the middle, and then it finally is delivered to the consumer, and you can see there's a question there. It's important to note that the questions are not directly tied to any one curriculum, so this isn't out of the grade 9 curriculum or the grade 10 curriculum. The test is being written by grade 10s, not necessarily grade 10 science students. So if in your school you happen to have grade 10 science students or you happen to have grade 10 students who have done science in some different order, they will still be writing this test at the end of their grade 10 year, whether or not they're in a science class. So again, if you read down through there, you can see a lot of the information is given in the question. As I say, there was even a little bit more info that I cropped out of this when I lifted it out of the PISA style test. So I want to kind of leave that behind the science test itself. If you have more questions, feel free to contact me. It's just darren.white@nbed.nb.ca. I have more information that I can pass along to you, and as I say, if you need more info, just get in touch, and I can sit down with you and take a look at what that administration of that grade 10 science test might look like in your school. I want to go on though now and take a look at what, think about what your best science classes looked like. If you think back to your last 2 or 3 years of teaching and you had those great science classes where everything was going, you just hated to see the class come to an end, what did those look like in your class? be interesting to see how that compares. This was a contract that was drawn up between a teacher and their students, where the students came up with what they wanted to see when they were doing science, and they wanted to see things like hands-on investigations. They wanted to investigate questions that made them think. They wanted to learn together collaboratively and learn from each other. They wanted the teacher to be enthusiastic and knowledgeable. They wanted some great resources. They wanted to have familiar contexts that they recognized and they could relate to. And they wanted to have outside experts, visitors from outside the school, and be learning outside of the classroom as often as possible. So interesting to look at that, and I suspect that some of those things would have percolated to the top when you were thinking about what those great classes in your experience have looked like. So one of the challenges, I guess, is to move from left to right along this arrow. Often when we started out teaching, or at least when I started out teaching, I thought if I could get them to remember something, to reproduce it on the test, I was doing my job. And at one point that was sort of the role of the teacher. But information has become so cheap nowadays. You know, most of us now carry around a cell phone that gives us access to tons of information anytime we want it. So that remembering piece is very easy to come by now. And we want to sort of move along towards the understanding and the applying and the analyzing, and ultimately to get them to be able to evaluate what they've seen and create new content. So that's the challenge. And I found this TED Talk that I thought is fairly apt, because the fellow does have a science and engineering background, and he talks about what sort of turned him on to science.
This is a Formula One race car. It is one of the finest pieces of engineering in the entire world. It goes 0 to 60 in 2 seconds, has nearly 1,000 horsepower, and cornered at 4 Gs, so hard you can barely breathe. But it's not just a fine piece of engineering, it's also incredibly exciting. So exciting that tens of millions of fans around the world gather around every week and watch this race around the track. I myself, as a 10-year-old boy, was one of those fans. And it ended up inspiring me to study engineering, to try and figure out how does that work, why does it go so fast, what is it made out of. And throughout my course of engineering at Dartmouth College in graduate school and undergraduate, I found myself leading a race car team, building a car like this, and studying equations like we see here about the vehicle dynamics, the suspension geometry required to achieve that. Understanding how to make a part of steel tubing incredibly strong so it wouldn't break because we're building a race car, but also incredibly light because we're building a race car. And I spent night after night getting deep into these formulas. But it was all exciting and worth it because we were building a race car. Now imagine if my parents had forced me to memorize this equation of angular momentum and torque and how they relate before allowing me to watch a Formula One race. Now it seems funny and crazy, but that's exactly what we're doing in education. We're forcing students to memorize seemingly irrelevant and mundane and boring details before allowing them to see the beauty and excitement intrinsic to every subject that they're about to study. And this is backwards. So why are we doing it this way? Well, it's not because we don't care. The fact in education is that education is created by experts. And experts suffer from the curse of knowledge. And the curse of knowledge makes it difficult for experts to understand how the beauty of the subject that got them excited in that subject in the first place, without understanding every last detail that they're now so deeply involved with. And this curse of knowledge has a negative impact on education. Carl Wyman notes that well-intentioned physicists are achieving poor educational results because the curse of knowledge makes it very difficult for them to understand how physics is best understood by the novice student. And the result of this curse of knowledge, the result of the fact that education is created by experts, is a very boring curriculum. We start with details. And we bore students and make them memorize, again, seemingly irrelevant facts because they have no context for those facts and figures and dates. And then we try and force them to get into some more advanced and intermediate topics and try and force them down this learning path that we think is right. And then, if we haven't bored them to death, they get to see and appreciate some of the big ideas that make each subject so exciting. And what we need to do is flip this entire curriculum. And we need to start with the big ideas. Because when you start with big ideas, you do two incredible things. One, you give students a great context and relevance and meaning for the subject they're about to study. And you also create inspiration and motivation, the type that inspired me to study engineering. And then, when you have this context and motivation, you're able to create a natural and a not forced learning path. Because that excitement, that motivation, leads you to ask questions. How and why? And then, by answering those questions, you get to organically build a very deep knowledge and a deep expertise that's required in any particular field. Because you need to understand the formulas to make sure that car doesn't break, yet goes as fast as possible. Now, this idea of inverting the curriculum is broader than just a classroom. Yet we have seen research that shows that it works on a classroom setting. For example, a study at the Stanford Graduate School of Education took two groups of undergraduate students studying neuroscience. And in one, they did the traditional method of reading a text, then doing an exercise, and then taking a test. And in another group, they let them start with a hands-on exercise about what they were about to learn. And what they found was that the group that started with some context, some motivation, some exploration, performed 25 to 30% better. Now again, this is on a classroom setting, and what I'm talking about is taking the underlying ideas that make this effective and applying that to the entire curriculum on a year or multi-year approach. Let's take biology, for example. Many of us in this room probably took introductory biology in high school or college. And you may remember a diagram like this, a eukaryotic cell. And you should remember it because it dominates the first few chapters of any biology textbook. And you look at this scary-looking diagram with words you can hardly pronounce, and you may think to yourself, what the hell is a rough endoplasmic reticulum? And why should I care? Well, a group of biology professors at Grinnell College had that same frustration. And instead of forcing these students to go through a curriculum of prerequisites in biology and chemistry and microbiology, they thought, why can't we invert the curriculum? What happens if we give students a glimpse of how beautiful biology really is? And they created an introductory course that did exactly that, that started with real-world research challenges, with topics for an introductory course that sound like phenomenally interesting TED Talks, the sex life of plants, biological responses to stress, how to build an animal. And this is an introductory course in college that got students excited about biology. And what they found was that this introductory course helped both ends of the spectrum. They found that students who were never going to end up majoring in biology were able to appreciate the beauty of biology and then go on to appreciate that in other walks of their life. And they helped some students find a love for biology and go on to be biology majors and researchers and scientists. And if you take this back to the textbook example, we need to take that textbook and completely invert it. And instead of starting with the eukaryotic cell, we should start with what biology really is, which is life itself. And what makes life so interesting is because we have this very rich ecosystem and ecology. And what makes our ecosystem so rich? The fact that we have an incredibly diverse array of plants and animals. And how do we get to those diverse plants and animals? Because of evolution and different evolutionary strategies. And what makes evolution function? Genetics and genes. And what underpins genes? DNA. And how does DNA replicate? And what makes it possible? The eukaryotic cell. And what the hell does a rough endoplasmic reticulum do? It helps facilitate protein folding, without which none of us would be here. So if we think about what we can all do to start implementing the idea of inverting the curriculum, and it starts with students. Keep asking why. Don't let our education system beat the curiosity out of you. Continue to ask for meaning for the subjects that you're studying. Parents, when you're at the dinner table talking to your kids and asking them what they studied in school today, tie that to some real-world example in their life. Create that context for them. Administrators, let's think beyond standardized tests. Let's give teachers freedom to implement some of these ideas. And finally, teachers, let's get back to the passion and excitement that got you excited about teaching in the first place. Let's not scare away the next generation of great scientists and engineers and authors by making them memorize irrelevant, boring, and mundane facts before letting them see the beauty of those subjects. And take this not just in a class setting, not just a week in the start of the class, but push to apply these learnings and this idea to your entire curriculum. I'm sure glad that my parents didn't make me memorize those formulas before letting me watch a race, because it changed my life. And it led to this, being able to drive a race car that I helped design and build. And that's exciting. And so is education. And we need to show that to students. We need to help make education more relevant and exciting for all students by starting with big, beautiful, exciting ideas and inverting the curriculum. Thank you.
So I have a bit of a love-hate relationship with these TED Talks. You know, they're great and they sound so easy. And yeah, why wouldn't we just flip the curriculum? It makes so much sense. Well, you know, we have some challenges that make it a little harder than what would be implied through a TED Talk with getting these skills out to the students. And the first is subject knowledge. You know, if we're not 100% confident with 100 different types of topics in science, and who is, then letting go and letting the students go down these roads if we don't know where they might end is a bit challenging, and definitely you know, keep some of us from going to the full extent of what the TED Talk would suggest. But aside from that, there's more practical challenges that we run into all the time. We have a huge range of students in our classes, and to be able to differentiate, to provide support for the least able students while still challenging the most able students in our classes is a real challenge. One of the challenges I always had when I was teaching was laying out science investigations, and I wanted the students to get the right answer. So I would give them the procedure, and I would make sure that they measured out exactly 10 milliliters of this substance and poured it in at this time. And the results they got were exactly the results I expected, and also exactly the results that they expected. And that's not, they're not doing real science. They're following a recipe here. And I think back to my own days when I was a student doing labs, and I found myself in this situation a lot. I'd go to the lab. Sure, it was a great chance. You get out of class and you get to experience the lab, which was a little different. But a lot of times, even thinking back now, I have to think, what was it that I was trying to do in that day in the lab? The goals weren't clear to me by times. So we've got some definite challenges of things that we have to kind of work with here. So take a minute and just think about some things that you can do to make your investigations less directed, but making sure that the goal is still clear and understood. And here's one suggestion, one idea, is to use some models to check for success. So have some exemplars, lots of exemplars up around your class, and you can ask the students this. You can say, well, okay, which one of these is best? Now tell me why it's the best. Come up with 4 or 5 reasons why you think one of these might be better than the rest of them. Together, maybe you'll come up with something like this. Now, what makes a good table? Well, I used a ruler. I put a title on it. I used column headings and scientific languages, and I recorded the data correctly. They might come up with others, who knows? But the important thing here is co-construct this with your students and then that information will be theirs. It won't be yours, and they'll be able to carry it with them that much easier than if you're just giving them, here is a good table, and I want you to do it like this. So we're saying here, give them the freedom to explore science in the way it should be explored. But you can't just come in that first day in September and say, go do science, I will see you in June. You need to make sure that you know what they know, you find out what they know, and what they can do before you get started. You have to make sure that the goals, everybody has the goals in mind. You know what skills you're trying to develop, and everybody knows what knowledge you're trying to develop as part of the curriculum. And everybody has to know what good looks like. So that's the use of those exemplars, those models that we were talking about earlier. And again, if you can co-construct those criteria with the students, so much the better. And again, make sure that they're asking questions and not being afraid of asking a stupid question, or not being afraid of that failure. Because again, 9/10 of good science comes from those failures. So have them question everything. This, of course, all changes your role. My role in the classroom when I started used to be, I need to help the children get it right so my lesson is successful. And later on it became, I need to help the children learn so that lesson is successful. You're supporting learning rather than teaching. And as I said before, making those mistakes is at the very heart of learning itself. So that's it. That's all I've got. A couple of things to think about at the end of the video here. First of all, is there things that you can do in your classroom to make your science more skills-based? Can you assess those skills as part of your ongoing formative assessment regime? I would encourage you to take a look, as I said before, at things like the released PISA and PCAP exam questions. If you are looking for some of those resources, Google is your friend. They're out there on the internet. If you can't find them, shoot me off an email and I can send you the link or send you the document. And then, are there other supports that you need? If so, contact your SPR or again, fire me off an email. And if I can't help you immediately, I can track down some people that can help to move you in the right direction. But don't feel you're going at this alone. We can move forward with it together. So that's it. As I say, this is my first attempt at doing a presentation like this over YouTube. If you found it useful at all, let me know, or let me know what could be changed. If you absolutely hated it, you could let me know that as well. Well, maybe wait till Monday to let me know that you absolutely hated it. Don't ruin my weekend. But thanks for your attention, and I hope you have a great rest of the day and a great weekend.